Hey guys, we're picking up on slide 36 of the PowerPoint. We're talking about osmotic pressure, which is the pressure if you have two liquids separated by a semi-permeable membrane and only the solvent molecules can pass through. If you dissolve a solute on one side or the concentration of the solute are different between the two sides, that's going to cause a net flow of solvent molecules from one side to the other. Specifically, it's going to flow from the side with a higher concentration of water, which means less solute, to the side that has less water or more solute, okay? To be more specific, let's just say I have a container that has liquid in it. I put in a semi-permeable membrane. On one side, we're going to say we have pure water. On the other side, we're going to say it's 5% mass to volume NaCl. So in that case, we're going to have a pressure for the water to move through the membrane. Now, first of all, water will move both ways. Okay, water can flow either way, but the net movement, more molecules are going to move from the side where there's more water to the side where there's less water. It's essentially diffusion. Diffusion is the movement of particles from an area of high concentration to an area of low concentration. Well, if it's the solvent that's moving, then we're looking at the concentration of the solvent here, okay? In pure water, the concentration of the water basically is 100%. On this side, if it's 5% salt, that means it's 95% water. So the water is going to flow from where it's 100% water to the area where it's 95% water. Now, as that happens, if water flows through the membrane, again, both ways, but the net flow is from left to right, what will happen is the volume on this side will go up, and the volume on the water side will go down. So you actually will see a change in volume between the liquid on each side of the membrane. Okay? Now, that's kind of qualitatively what osmotic pressure is. We can also calculate a value for the osmotic pressure. The equation we use, typically pi equals mRT. This time it's capital M for molarity. R is the gas constant. Now, if you remember in chapter 11, we used the thermodynamic value of R, which is 8.314. For this equation, we're going back to chapter 10. The gas constant for that one was 0.082. That's the one that we plug in right here. And then the temperature needs to be in Kelvin. If we multiply M times R times T, that's going to give us the osmotic pressure. The units are based off of R. Remember, molarity is moles per liter. T is temperature in Kelvin. R, the gas constant, is liters atmospheres over moles Kelvin. If you cancel everything out, the pressure is going to come out to be in atmospheres. Okay? So that's our equation we're going to use if we're doing any calculations with osmotic pressure. So on slide 37, the first problem there, or the only problem on that slide, hemoglobin is a large molecule that carries oxygen in blood. We dissolve 0.263 grams of hemoglobin in 10 milliliters of a solution. We measure the osmotic pressure. It's 7.52 torrs at 25 degrees Celsius. Let's calculate the molar mass. This is the same problem we did earlier with boiling point. So let's do it again with osmotic pressure, because again on the test you don't know which colligative property we're going to use, but we're definitely going to do a problem where we solve for the molar mass. Okay? So first of all, when I'm plugging everything in, it has to be in the right units. So the pressure, I need to do 7.52 torrs. I need to convert it into atmospheres. So 7.52 divided by 760 is going to be 0.00989. That's my atmospheres. My molarity is what I'm solving for. If you remember in the first step, we're going to solve for the concentration. R is going to be 0.08206 liters atmospheres per mole Kelvin. And then the temperature, 25 degrees Celsius, put it in Kelvin, 298. So I'm just going to solve for molarity. It's going to be that. So I got the molarity equals 4.046 times 10 to the minus 4 molar. Now, step 2 of the process. Use that value to find the moles. Well, I know molarity is moles per liter. Again, moles is what I'm finding, so that's my unknown, that's X. The volume of the solution, the problem said it was 10 milliliters, so in liters that's going to be 0.01. So now if I solve for moles, X is going to be 4.046 times 10 to the minus 6 moles. All right, and then finally, molar mass. Step 3, it's the grams we dissolved, which was 0.263 grams, divided by the moles, 4.046. And then on the slide, it tells us that that should come out to be around 65,000, which, and when we think about molar masses, most compounds, the molar mass is going to be somewhere between 20 and 200 probably for most normal molecules, but this one's different. It's a protein. It's a biological macromolecule. So if you get that molar mass of 65,000 and think that doesn't look right, most of the time you'd be right, except this is a protein. Proteins are really big, so the large molar mass does make sense. All right, so next slide, the Van Hoff factor. Okay, so we've ignored something along the way. The Van Hoff factor, basically the equations we're using, the molarity is the concentration of the solute. Okay, now, not every compound is going to behave the same way when you dissolve it. When I dissolve glucose into water, every glucose molecule, when I put it in water, the crystal breaks up, but each molecule is only going to create one particle in the solution. Okay? If I dissolve sodium chloride into water, each NaCl, we don't call it a molecule, ionic compounds are called formula units, but each formula unit of NaCl, when it dissolves, the ions split. So from one NaCl, I'm going to get two particles floating around. Each ion is a separate particle. Okay? That's key because if I give you the molarity of sodium chloride and you plug it in for your M value, it's not going to match up with the data that you see because when the sodium chloride goes into solution, when it splits, we're going to have twice as many particles floating around as what the molarity would have indicated. So we're going to introduce another term into the equation that's called the Van Hoff factor. Okay? So what we do, again, we're moving on to another problem here. If I look at my equation, M stands for the molarity of the compound, but I'm going to put another term in front of it, I, which is the Van Hoff factor, that's going to be multiplied by the molarity of the compound. So for sodium chloride, when I dissolve it, I know that I should get two particles from every one of the formula units. So the I value for sodium chloride is 2. What if I did magnesium chloride? The formula of magnesium chloride is MgCl2. So how many particles will it break into? Well, when it dissolves, I'm going to get one magnesium, but then the two chlorines, or the chloride ions, are going to come apart separately. So I'm going to end up with a total of 3 particles coming out of one MgCl2 formula unit. So for this compound, the I value would be a 3. I would plug in a 3 right there if this was my solute. What about glucose? C6H12O6. What's the I value for glucose? Well, if you remember, I said when you dissolve glucose, each molecule stays intact. The crystal breaks up, but each particle is a whole molecule. and it floats around as one thing. So therefore, the I value for glucose is 1. So if I'm dealing with a normal a normal covalent compound that doesn't split, the I value is 1, which means you can usually just leave it out. But if you're dealing with an ionic compound or a strong acid, then you have to figure out how many particles it's going to break into, and then that becomes your I value that you plug in. Okay? Now, we are making some assumptions when that happens. If I dissolve MgCl2 in water, we're assuming that all the ions break apart every single time. That assumption is like an ideal situation. So when we say the Van Hoff factor for MgCl2 equals 3, that's called the ideal Van Hoff factor. It's pretty close to what happens in reality, but maybe not perfect. Okay? So the ideal Van Hoff factor for magnesium chloride is 3. In reality, you do have a few ions that kind of stick together. So if I want to know what the real Van Hoff factor is, I would actually have to do some experiments to determine, okay, when I dissolve a mole of MgCl2, I know how far down the freezing point should go. If it doesn't go down quite as far, I can set up ratios and figure it out. And I might figure out that actually from one of these, I might only get like 2.7 particles on average, or 2.8 or whatever. Okay, so those numbers there are tables online or in your book that you could look up to find the real Van Hoff factors. For the most part though, when we do problems, we're going to assume the ideal Van Hoff factor unless you are told otherwise. Okay, so the Van Hoff factor is mostly going to be a whole number based on the number of particles that it break into. All right, so let's move on to the next one. So I have, the next slide is a comparison. If I'm comparing 2 molar NaCl to 1.5 molar Na2SO4, which one would have a higher boiling point? Okay, so again, as I dissolve something into water, the boiling point of the water goes up. The amount is based on the concentration of the particles. So it doesn't matter what they are, we just have to figure out how many particles there are. Okay, well if the molarity of the compound is 2 molar, but then it splits, I want to know like the total concentration of all the particles. Well, that's kind of my I times M. That's going to give me the concentration of particles. So it's going to be sodium chloride, the Hoff factor is 2. The concentration is 2. So if I multiply those, the effective concentration is going to be about 4 molar. If I do the same thing for sodium sulfate, I times M. So the molarity is 1.5 molar. Think about what do you think the I value is going to be for sodium sulfate. How many pieces will it break into? Okay. The answer to that is when it splits, sulfate is going to stay 1 particle, but then I'm going to get 2 separate sodium ions. So I'll get 2 Na pluses and 1 SO4 minus 2. That's 3 particles. So it's going to be an I value of 3 times the 1.5. Again, that concentration, the effective particles are going to be about 4.5 molar. So, even though at face value, this concentration of the compound is lower, once it splits, we're going to have more particles in this solution. So this solution, the sodium sulfate, is going to have a higher boiling point. The boiling point is going to be elevated by more. Okay, so then the next question, which one would have a higher freezing point? Okay, well this one's a trick question. The one with the higher concentration of particles is going to have the higher boiling point because the boiling point goes up. It's also going to have the lower freezing point because the freezing point goes down. So this question is tricky. It says which one has a higher freezing point. That's going to be the one that didn't change as much. This one's going to have the boiling point, the freezing point won't be depressed as much as this one. This one's depressed more, this one's depressed less, so this is the one that has a higher freezing point, and it would have a lower boiling point. All right, finally brings us to the last topic, vapor pressure. So we talked about vapor pressure, again, dissolving a particle into the solution. So if I have a container, I have a liquid, a few of the particles start to escape up here into the air of the empty space above. Some of them go up, some of them come down. After a while, it'll reach a stable pressure. That's the vapor pressure. If I dissolve new particles in here, basically if we assume the solute is not going to contribute any more vapor. So again, that's a non-volatile solute. A solute that doesn't give off vapors. So like if I dissolve sodium chloride in water, any vapor that comes off is going to be water. The sodium chloride is not going to come out as a vapor. That's just not going to happen. Okay? So when I dissolve a solute in the solution, the percentage of the molecules that are the solvent are going to go down, which means fewer molecules are available on the surface to escape. So essentially the vapor pressure is going to be decreased. Vapor pressure decreases as I add solute. The equation we're going to use, again, if you look at the PowerPoint, there's several different ways you can manipulate the equation, but really I only like to use one of them. The one that I use is the one at the top of the slide in yellow. The vapor pressure of a solution equals the mole fraction of the solvent times the pure vapor pressure of the solvent. Okay, now, when we use this notation, the superscript 0 is called a naught, N-A-U-G-H-T. So P naught represents the pure vapor pressure of the solvent when there's nothing else in there. Okay, so that's the equation I like to use. So then finally on slide 42, we have a problem here. At 25 degrees, the vapor pressure of pure benzene is 93.9 torrs. A solution is made where the new solution has a vapor pressure of 91.5 torrs. What's the mole fraction of the solute? All right, so the pressure of the new solution they made was 91.5. Okay? The mole fraction, I don't know. That's the mole fraction of the solvent. And then the pure vapor pressure, they told us, benzene's vapor pressure normally should be 93.9. Okay, now, the units of pressure don't matter as long as they match. It has to be the same on both sides. Okay, so I'm just going to divide this one over. The mole fraction of the solvent is going to be 91.5 divided by 93.9. 91.5 divided by 93.9. So that's going to be 0.974. Okay, now the question actually asks for the mole fraction of the solute. We have the mole fraction of the solvent. If you remember at the beginning of all the concentration unit section of the video, I mentioned that the mole fractions are easy to do. If you get one of them, the other one is just 1 minus that number. So if this is the mole fraction of the solvent, if I just do 1 minus that, it'll tell me that the mole fraction of the solute should be 0.026, which that is what's on the slide. So that's the answer to the question. Okay, I believe that's it. So we're going to cut off the videos for chapter 13.